Let's be real, we've all dreamt about it, right? A powered suit of armor that gives you superhuman strength, just like in the movies? It's an awesome idea. But what does it actually take to build one in the real world? Well, let's dive into the incredible journey of turning that sci-fi dream into actual hardware and uncover the single biggest challenge that engineers are still trying to solve today. And this just says it all. On the left, you've got the fantasy. Sleek, powerful, perfectly fused with the human body. And on the right, well, that's the 1960s reality. This was one of the very first big attempts at a man amplifier. And you can see there's a massive gap between the dream and the actual nuts and bolts of making it happen. Okay, so first things first, let's get on the same page about what we're even talking about. An exoskeleton isn't just a suit of armor you climb into. The absolute key idea, as you see here, is that it's a machine you wear that is physically connected to you. It's not just protecting you, it's directly transferring its power to your body, making you stronger. And it's really important to draw a line between this and a couple of other things you might have heard of. So a prosthetic, that replaces a missing body part. An orthosis, like a knee brace, that assists someone who has an impairment. But a true exoskeleton, that augments the performance of an already able-bodied person. The goal is to make them stronger, faster, or more resilient. So let's rewind the clock. Let's go back to the very beginning. Back in the 1960s, the goal was super simple and incredibly ambitious: to build a man amplifier, a machine that would literally multiply a human's strength. And this was their masterpiece, the General Electric Hardeman. This was a 1,500-pound beast of a machine designed to make lifting 250 pounds feel like you were just lifting 10. The way it worked was with this master-slave system, so the operator's suit was the master, and this huge, powered slave suit on the outside would mimic every single motion. The power it could unleash was just immense. But, and this is a huge but, there was a catch. The Hardeman was so powerful, and its movements were so jerky and violent, that it was actually too dangerous to test with a person inside. I mean, just imagine a 1,500-pound machine thrashing around completely out of control. This was the first great lesson of exoskeleton design. Brute force is useless, and frankly, it's terrifying, without control. So that terrifying lack of control, it sent researchers straight back to the drawing board. They realized the next step wasn't about adding more power. It was about finding more control. This whole new era was all about shifting from that brute force approach to one of finesse, figuring out how to make these machines work with the human, not just on them. And where do you turn when you need precision? Well, you turn to space. NASA started looking into exoskeletons to help astronauts on spacewalks. See, the gloves on a spacesuit are super stiff, and it takes a ton of effort just to move your fingers. So the idea was to build a small, powered exoskeleton for just the hand, to make those tasks easier. This required delicate, precise control, the absolute opposite of the Hardeman's raw power. So that early work, combined with huge leaps in computers, materials, and batteries, brings us to the modern era. And this is where we see an absolute explosion of innovation, with exoskeletons branching out into all sorts of incredible new directions. And when I say an explosion, I am not kidding. Just look at the research. Back in the 70s, you had maybe a couple hundred papers a year on this stuff. By 2017, that number skyrocketed to almost 7,500. This isn't just steady growth. It's a technology finally catching up to a 60-year-old dream. Today, all that research is heading down two main paths. The first is augmentation, which is kind of the direct descendant of that original Hardeman dream. Suits like this one, the Raytheon XOS-2, are built for military and industrial jobs, letting a soldier or factory worker lift heavy things over and over again without getting tired or injured. The second path, though, is rehabilitation, and this is where things get truly life-changing. Devices like the ReWalk exoskeleton are allowing people with spinal cord injuries to stand up out of their wheelchairs and actually walk again. You see, this isn't about making someone superhuman. It's about restoring a fundamental human ability. It's incredible. And the technology just keeps evolving. The future might not even be made of metal. This here is a soft exosuit. Instead of a heavy, rigid frame, it uses flexible fabrics and tiny sensors that are literally woven into what's basically smart clothing. It's lightweight, and it works by giving your own muscles and joints a gentle boost, not by replacing them with some bulky machine.
But here's the thing, whether the suit is a giant metal frame like the XOS2 or it's made of smart clothing, they all run into the exact same fundamental problem. And this is maybe the most important takeaway from this entire journey. The hardest part of building an exoskeleton isn't the machine, it's us. It's the incredibly complex human being you're trying to put inside it.
Think back to the Hardman. This is basically the same problem, just on a smaller scale. This early robot arm was strong enough to lift a chair, no problem. But it had no sense of touch. It couldn't feel the difference between a gentle grip and a crushing force. This right here is the core challenge. Bridging that massive gap between what the person wants to do and what the machine's raw power actually does.
To really get why this is so hard, just look at your own hand for a second. It has over 25 degrees of freedom. That's all the different ways your joints can bend and twist and turn. Now, imagine trying to build a machine that has to perfectly match all of that complexity in real time without ever getting in your way. It is a mind-boggling engineering challenge.
And that complexity leads to all of these key hurdles that every single designer has to face. For one, batteries are still heavy and they don't last very long. Then you have ridiculously complex joints like our shoulders. How do you even begin to replicate that mechanically? Plus, every human body is different, so how do you design one suit that can fit everyone? And, maybe most important of all, safety. How do you guarantee the machine will always move with you and never ever against you? So, how in the world do you solve all of these problems at once? Well, engineers realized they couldn't just keep trying to build better hardware. They needed a completely new way of thinking about the problem, a better blueprint for the design process itself. Yeah, the old approach, build a powerful machine and just strap a person inside, it was completely backward. To solve these fundamentally human problems, the entire design process had to become human-centered, right from the very beginning. And this led to formal, structured methods like this one, called Quantum X. Now, the order of operations here is everything. Notice you don't start with motors and gears and metal, you start with the person. You analyze them, their task, their environment. You create these complex biomechanical models of their body. It's only after all of that human-focused work that you even start to design the hardware. And then, of course, you test it with real people to see if you actually got it right. Really, the whole goal of a process like this is to take the guesswork out of it. Instead of just building a machine and hoping it works with a person, you follow a clear set of rules that are grounded in the science of the human body. It's about moving from trial and error to a true science of human-machine integration. Which brings us right back to the beginning. From that clumsy, dangerous Hardeman in the 60s, all the way to the soft, intelligent suits of tomorrow, the journey has always been about one thing: closing the gap between what a human wants to do and what a machine does. So the ultimate challenge, it turns out, isn't really about building a better robot. It's about better understanding ourselves. And that leaves us with the critical question, not just for exoskeletons, but for all future technology. How do we design it to truly fit the complex, messy, and incredible human inside?